So, welcome back to lecture number 19. So, in this lecture we will see the other processes which are covered under metal matrix composite. There are few doubts which students have asked. So, based on their doubts, I just wanted to put first 3 slides explanation on some of the concepts which we have to know very clearly before making these processes. The first thing is interface. They have asked what is the difference between interface and interface. So, I thought let me explain to them, because these two terms are used, swapped and used many a times, and many people make mistakes while using these terms. This interface, why is this interface very important? Because this whatever is there is the reinforcing agent. It can be a ceramic, it can be a metal, whatever it is. So, this property is material property is different, and this is a matrix property which is different. So, between these two A, but that means to say this is A material, B material, between these two persons there has to be an interface. This interface is nothing but a boundary, and this boundary we should have a proper locking or proper adhering between the two surfaces. If we do not have, for example, I have a reinforcing agent, and let us assume I have a matrix something like the sitting. So, in between there is a void space. So, now this particle ceramic can easily come out, and second thing is the addition of the ceramic which is going to take the load will now never take the load, because the load is not getting transferred from the matrix to the fiber. So, this is interface. In composites what we are discussing is we would like to have intact interface. So, let it be metal matrix composite, let it be ceramic matrix composite, let it be polymer matrix composite, thermoplast, thermoset, let the reinforcing agent be fiber, let the reinforcing be particulate, or let it be whisker. Anything you take, you should make sure that it has a proper interface. If the interface is weak, then the composite whatever you have fabricated will not work to your expectation, or it might have early failure because of this interface problem. And how do you enhance the interface? I will understand what is material A properly, I will understand material B properly, and then I will try to do some gelation in between A and B. That means to say I will try to functionalize A such that it tries to make a proper interface with B. So, now what happens? There is in between a coating. In glass fiber I said silane coating, in metal matrix composite when I said the agglomeration has to be avoided. So, we try to functionalize the particulate. So, all these things are done to make sure you get a proper interface. So, this is the zone across which the matrix and the reinforcing phase interact physically, chemically and mechanically. Interestingly, last class I was discussing about a scanning electron microscope. If you are going and if you want to understand still more finer details, if you see in metal matrix composite there are a lot of beautiful images which are available in the literature, which talks about a very good mechanical locking between the ceramic particle and the matrix. And by the way, it is not only functionalizing the particulate we do, we can also add alloys. For example, silicon is added and you can add alloys, and this alloys what we do is we can add alloy and make sure that it does a proper wetting. So, this interface is predominantly to make sure that there is a proper interaction between the matrix and the reinforcement chemically, physically and mechanically. And for composites this interface is very, very important. Okay. So, this is a direct bonding between primary and secondary. This is another interface. There is a spelling difference, interface PHASE, phase, different phases which we see in alloys, in metals. Right. So, this is phase. So, in this case a third ingredient, this is what I said, you functionalize. A third ingredient is added to achieve a bond between primary and secondary. So, what is the disadvantage of this fellow? Naturally, you have to have a small sacrifice in the mechanical properties. So, this is nothing but you add a third ingredient which will try to functionalize this green ring, which will try to functionalize the particle, and then you try to have a proper adhering. So, in some cases the third ingredient must be added to achieve bonding of primary and secondary, which is called an interface. This can be brought by coating, this can be brought by reaction depending upon the choice. So, now I have made it clear interface and interface. We would love to have this first, and if it does not happen, we would love to have this. But whatever is said and done, there has to be a proper interaction either chemically, mechanically or physically between these two. The next point, and so here I have just put the SEM figure so that you can understand what is that. So, we can see large. Why is this difference coming? Why is this interface very important? Because the alloy whatever you choose has a different set of mechanical properties, physical properties, and the particulate whatever you choose, that also has a different set of mechanical, physical properties. Okay. So, because of this difference in properties, and when you want to ask these two fellows to join each other, they have this interface problem. Okay. The interface bonding can very strongly influence composite strength, modes of failure. I will tell you, if you have a matrix, a reinforcing agent, and if a crack is propagating, so what happens is this crack strikes the reinforcement, and then the energy is getting distributed over the, this is the ceramic. So, you see it gets distributed over, the energy is getting distributed over the surface, and what it does is it tries to break the interface, and the energy gets distributed. So, what happens is the crack propagation is stopped. So, the modes of failures are changed, or the modes of failures have a strong influence on the interface. Young's modulus has, interlaminar shear strength has, compressive strength, environmental resistance. If it is open and water can go inside, it starts reacting or corroding, whatever it is, it tries to weaken. Structural stability at elevated temperatures also goes down. Fracture and fatigue behavior also falls down drastically if we have a very poor interfacial bonding. So, now it is clear that interface is very, very important. The next thing which I was talking again and again, let it be thermoplastic composite, let it be thermoset composite, let it be metal matrix, ceramics, which we will see later. So, all these things basically depends upon a property called wetability. Wetability means how good the polymer can spread, or can the matrix spread around the reinforcement. If we have very good wetability, then naturally you will have a very good interfacial bonding. If you have very poor wetability, and suppose if the polymer or the metal does not wet the ceramic, so then it will try to roll off like this, and you will have very poor wetability. So, it defines the extent when a liquid will spread over a solid surface. This is wetability. So, wetability in lotus leaf you would have seen. So, this is, and this is now, this idea is duplicated or mimicked in lot of engineering applications today to avoid corrosion. Right. So, in metal matrix composite, they make very small textures on the surface, and then the water droplet does not stick on to the surface. It changes from film condensations to drop wise condensation. It rolls off and there is no corrosion. Okay. A good wetability means a liquid matrix will flow over the reinforcement, covering every lump and dip on the rough surface of the reinforcement and displace all air. So, for this property, for polymers to some extent it is easy to achieve, but when you do metal matrix, you are trying to take the temperature of the metal alloy to a higher state and convert it into a liquid. So, viscosity plays a very important role. So, this wetability in turn is linked with that, and then it tries to wet the surface. So, wetting will occur if the viscosity of the matrix is not too high. Again, it is a relative term, there is nothing called, because it depends on the combination you choose, and interfacial bonding exists due to adhesion between the reinforcement and the matrix. So, I have said theta is the contact angle. So, people try to measure it by using contact angle experiments. So, this they always talk about angle, the angle should be greater than 90, angle should be greater than 180. They keep talking about all these angle. What is this angle? This angle is nothing but a wetability angle, or it is called as contact angle. So, if the theta is 180, so no wetting takes place. If it is 180, no wetting takes place. If it is between this, if it is 0, it is perfect wetting. We would love to have it. If it is falling between 0 to 180, then the degree of the wetting increases as the decrease in the theta. So, there are a lot of people have done lot of experiments, and they have found out for various combinations. It depends on the solid what you take, it depends on the liquid what you take, in the ambience what you place. So many things come into existence. That is why you see, when we talk about metal matrix composite, last class when we are discussing about diffusion, when we are trying to talk about squeeze casting, and we were trying to infuse metal inside the reinforcement, we said there is one more factor called as atmosphere which is present. The atmosphere also tries to play a role changing the wettability property. So, these are certain things which I thought I should share with you, because there were a lot of queries asked by students, what is interface, how is it defined, and what is wettability. So, I thought I will explain to you and then go back to my lecture series. So, last class what we saw was, different types of liquid state fabrication in making metal matrix composite. So, this class we will try to focus predominantly on solid state fabrication. That means to say, I will not change the state, solid state, I will use it as a solid state of a metal, and still I would like to make a metal matrix composite. Again, just for a repetition, the reinforcement can be in terms of a mat, the reinforcement can be in terms of particulates, or a lump of particulates joined together and then they form a given shape. Okay, so, what we do is we take particulates of maybe ceramic, and then what we do is we try to add some wetting agent to it, then we try to consolidate, we call this as a green compact, and then what we do is this green compact we slightly burn it. So, all the binders what we have added gets vaporized and it evolves out, giving lot of space for now when you pour a metal to enter inside. Okay. So, those things are called as preforms. So, preforms of ceramics are made, and then you try to have some voids there through which the liquid diffuses inside. So, today what we will do is we will try to see solid state, and then we will also try to see in situ fabrication of MMC. That means to say, when we try to add two ingredients, it reacts of its own and it makes both of them distinct and it evolves. So, the other way is co-deposition method. We would like to talk about electrolytic co-deposition, spray co-deposition, and vapor co-deposition. So, this is what we will try to cover in this lecture. So, processing methods, we had liquid state, last class we covered stir casting method and infiltration method. So, now what we will do is we will get into solid state. So, solid state we will try to see diffusion bonding and sinter forging. In solid state fabrication, metal matrix composite, here the metal matrix composite are formed as a result of bonding matrix metal and dispersed phase due to mutual diffusion occurring between them in the solid state at elevated temperatures and pressure. Okay. So, this is what happens here. So, here we will try to take as a result of matrix bonding of matrix material and dispersed phase. Right, dispersed phase is nothing but a reinforcement due to mutual diffusion occurring between them in solid state as well as in solid state at elevated temperatures and elevated pressure. The low temperature of solid state fabrication when compared to liquid state of the is undesirable here. So, here the temperatures what we use in solid states are very high as compared to that of your liquid state. So, metal matrix are formed after sintering operation, and they are done by rolling. What we do is once we make a crude bulk form, then we try to do a secondary operation to make sure that the composite is formed and the matrix and the reinforcement is uniformly distributed. The deformation operation can either be done in cold or in hot. So, there are two principal groups of solid state. One is diffusion bonding, another one is sintering. What is diffusion bonding? Diffusion bonding is a solid state fabrication method in which a matrix is in the form of a foil. So, we take a foil, then we try to put some reinforcing agent whatever it is, and then we try to have one more foil, then we have reinforcement. So, this is a cross section view. So, we have reinforcement. So, diffusion bonding is a solid state fabrication process in which we take a matrix. This can be in the form of a foil or a thin sheet. So, what we talk about is less than 100 microns. Okay. So, this is these are the reinforcements. So, now what you do, you keep a foil, then you keep this long fibers or mat or a preform of ceramic whatever you have made, you keep it here, and now what you do, you try to apply pressure, and then you also try to apply temperature. What happens if you just apply pressure? Yes, things can happen, but the only thing is you will try to you will still not get a proper consolidation. In order to have a proper consolidation, you go back and remember the wetability property. If you want to do that wetting property, then what you do, you try to melt this fellow to some extent, and then it tries to take a shape. So, temperature and pressure both are applied in a die or directly on a component, so that they get it. Generally they do not directly apply, but we try to apply in a die, and the die gives the shape of the metal matrix composite whatever you want. So, here interestingly you can also have functionally graded materials. So, what is functionally graded materials? Where in which along, suppose this is the core, this is the top. So, at every layer there is a gradation in your property whatever you want. So, this is a gradation in the property whatever you want. Okay. And this is the thickness. So, you take this as the thickness, and this is what is the thickness I am talking about. Okay. So, this is a property which gets deteriorated. So, if you want to make functionally graded material of different metals, for example, one zinc foil I can keep, one aluminum foil I can keep, one silver foil I can keep, depending upon your application you can start doing it. So, you can have a finished laminate of a composite material having multiple layer structures. The diffusion bonding is used for fabrication of simple shape parts, and here you can also integrate with another part. For example, you can add one more part which is a third part which is to be added to the composite, and you want to integrate it as part of this composite, you can still do it. For example, you take a rubber tube and then you wanted to have a nipple which is to be integrated. In the same way, then you can also try to add the nipple here, and you can have this metal matrix. So, you can try to make integrated parts using this diffusion bonding. So, this is what is diffusion bonding. So, I take this is the die on top surface, this is a die bottom surface, and here it is a flat die, and here you see that I have taken several layers. So, this can be exclusively matrix, this can be matrix, and then you have dispersed reinforcement. This can be dispersed reinforcement. Again, here you can play with the dispersed reinforcement volume fraction. For example, you can have 10% volume fraction. As and when you keep going, you can have 30% volume fraction here, and then on top you have a matrix whatever you want. So, now what you do when you try to consolidate and try to develop it, you will try to have a metal matrix composite which is functionally graded. So, functional gradation can be brought in while making it. And why is it very important? Because today when we are talking about multi-sensor applications, multi-sensor integration, all these things, so we always look for functionally graded materials. So, here is a stacking, and again the stacking you can also have your own sequence. You can have your own sequence in stacking, so that you try to get what is it. And once you stack, you make a large piece, then you cut to the required space, to size and shape whatever you want to get the required output. So, here the important parameters are temperature, pressure, of course time is also there, okay, and then you can also try to have volume fraction changing layer by layer. Okay. But this cannot be done in your stir casting method if you want to have functionally graded. But there also, if you are very wise, you can do it. So, what you do is you start dispersing higher density ceramic in the first, then lower density ceramic. So, again you can still have a functionally graded metal matrix composite, provided you think little and start working on it. So, this is how it happens. These are all the fibers. You can have fibers made out of metal you want, you can have fibers made out of ceramic you want, and then try to get whatever you want. Okay. So, this can be, fibers can be organized in some pattern, it can be random in nature also. So, the next bonding process is called as sintering. So, sintering is a process wherein which you start with metal powders, or you start with any powder, metal powder or ceramic powder, and you try to consolidate them. And here when you try to consolidate, you let us assume you consolidate only by pressing, then what happens, all these particulates, whatever was there, powder was there, it gets consolidated. Now, when it gets consolidated, you see there is a small space getting formed, and you wanted to still close this space. How can you close it? One, you can push in something there to close it, or you try to apply temperature. So, when you apply temperature, the consolidation happens in a big way. So, if you have a ceramic material which is of very high temperature, then what do we do is, naturally we try to go for a interface. We try to give a coating and then try to join it. If not, you have to think of a very high pressure, very high temperature, and then do it. I do not want to apply temperature. So, naturally our pressures goes extremely high. So, that is why people do in hot press, they do it in cold press, they do hydrostatic pressing, all these things are tried. If you can do both, that is good. If you have only one parameter to do because of some constraints in the material, so then the other fellow, if it is not there, the pressures have to go phenomenally high or temperatures have to go phenomenally high. So, you have to think of an equipment for it. The sintering fabrication of metal matrix composite is a process in which the powder of the matrix material is mixed with the powder of the dispersed phase. So, here this powder whatever we have taken here, you can think of taking only exclusively metal, or you can try to take exclusively ceramic, or you can try to take a mixture of both. I take all the prerequisite prior, mix it properly, maybe in a ball mill to get uniform mixing. I mix it properly and then I try to consolidate. So, I then put it in a die and then apply pressure so that I get a proper consolidation, and then I try to get this porous structure. Okay. So, you can do it in two stages. You can do it if you do not want to apply temperature, it is called as cold or it is called as green, right. And then if you want to apply pressure, temperature both, then you get the original output itself. Okay. So, here the dispersed phase in the form of small particles or short fibers. Generally, we try to use particulates, alumina, SiC, or we can also use whisker, and then finally you sinter it and then you try to get the output. In contrast to liquid state fabrication metal matrix composite, sintering method allows to obtain materials up to 50% dispersion phase. So, what is the advantage? Here the density goes very low. So, it becomes a lightweight material which can be thought of for high structural applications. You can also try to enhance the toughness if you want to a large extent. Okay. So, all these things go. So, where we were struggling to get in solid state in stir casting method 30%, 40%, we were saying that 50% can be done, but here in sintering you can easily go from 50% to 70% depending upon your requirements. You keep playing around, and when you try to do it, so the particle size is also very important, particle size, because particle size in turn influences the surface area. So there is a ratio called the surface to volume ratio, which I have been repeatedly telling, which plays a very important role. Surface to volume ratio. So particle size is very important, and the volume is also very important, so that you try to get the best out of it. Sintering, a primary driving force for sintering is not diffusion of material. If you look at this figure, you can see here there is a surface diffusion phenomena happening, there is an evaporation condensation happening, then there is a grain boundary diffusion happening. So here is a volume diffusion happening, and this is the grain boundary, and this is the plastic flow happening. So all these phenomena happen during the sintering process. So volume diffusion, grain boundary diffusion and plastic flow are the three major things which are involved in sintering. So around the surface you have surface diffusion, then you will also have the grain boundary getting formed, and you will also have evaporation condensation also happening. So these three are very important. Please make a note: volume diffusion, plastic flow, and the third one is grain boundary diffusion. All these three phenomena together happen to this sintering process. And if all these things are metal, the mechanism is going to be easy. If you have one particle as ceramic and the other two as metal, then the strategy has to be different. So these are the stages, different stages in which the grain boundary grows. So the different stages are: first you will have point bonding happening, and then next thing what will happen is this point tries to grow and then becomes a neck, and then this neck, when it starts growing, the pores gets shrinked, and further if you go to the next stage, there is a grain boundary getting formed along the particle grain size, so that the pore size goes much smaller. Generally these are the four stages which are involved in sintering process. So first is point bonding will happen. The point will, so this is a point, then the point becomes a line, or then slowly line or a surface, then it becomes more of pores. Okay, these pores are reduced and then you get a grain. So this is how, these are the four stages which are generally involved in sintering process. So I told you earlier also, if you want to do a sintering process, you cannot have direct ramping in of the higher temperature. We divide it into three stages. So the first stage will be preheating. So preheating will try to take it to a certain temperature, not exactly towards the melting, slightly less than the melting point. We try to take the temperature and maintain it there. So that what happens, if at all you have water molecules will go off, if you have air which is there, any oil, volatile oil which is there, all these things in the ceramic particle or in the metal powder or in the dye will all be just evaporated, clean, and so you try to maintain a uniform heat distribution. Then once the preheating stage is over, then we start our sintering stage. In the sintering stage, we ramp up the temperature to such a level. So ramp up the temperature with respect to time. You see, it is not done instantaneously, it is slowly done. So we try to take it to a higher temperature, and then we try to maintain it for some time. And then what we do is we switch off the furnace and allow to have furnace cooling all along. So when we do the furnace cooling, so that the particle does not, the product whatever is made, it does not have any cracks, which are induced by thermal stresses. This is what we try to maintain. So this is the heating cycle. So this graph is very important. As I told you, in any furnace, this graph is very important: temperature time profile. They will always ask, can you show me the temperature time profile? If at all a component fails or a product fails, they always try to dig out and take the temperature time profile of the heating cycle, and then they try to figure out where was the mistake. Okay. So, this is the furnace which is used or this is the heating cycle which is used for sintering process, and the sintering can be done by hot pressing, it can be done by hot isostatic pressing. So, hot pressing means it is only pressing from two directions, isostatic means all along you apply uniform pressure so that you get a sound output. Then you can also have hot powder extrusion fabrication of MMC. So, these are the three processes which are done under sintering for metal matrix composite making. So, in hot pressing what we do is we try to put a powder. So, in this powder what we do is we try to take a metal powder as well as a reinforcing powder, we try to mix them properly and then we try to put it in a die and then compact it. Okay, we try to put it in a die and then compact it. So, then what we do is we apply hot pressure. Hot pressing stage means we try to apply heat here, pressure is applied, heat is applied, heat and pressure is applied, and then finally what we get is an output. So, this process is called as hot pressing. Here the pressing happens only in the two directions, and since here it is a confined, it is a die, it is a confined portion. So, here we do not apply pressure. So, we make sure that it is a confined volume. So, it is we get a uniform strength distribution all along. So, if you do not do a proper mixing, then what will happen is you might have cracks which are there inside, which is very difficult for you to visualize. So, I am talking about not on the surface, the cracks inside. So, this will lead to poor quality output. Next one is hot isostatic pressing. Hot isostatic pressing is whatever was the deficit there. For example, I felt that in these directions there is no pressure applied. If the pressures are not applied properly, there might be a problem that at these places the compaction is not proper. So, in order to avoid this and try to get the best out of it, we try to do hot isostatic pressing. In hot isostatic pressing, the powder along with the mixture is put inside and then we put it inside a die. This die can be a flexible die. So, what we do is we put it inside and then we try to apply hot air or very high pressure around it. So, now what happens, there is a proper consolidation happening and you also get the required output, quality output. So, here proper consolidation is very important. Again here it is not necessary that directly you put the powder is not directly put into hot isostatic pressing. They go a green compact where they give a shape and a few consolidation happening and then they go to HIP. This is very good compared to direct going, this is very good. Okay. So, people try to prefer this and then get it done. So, here what is the biggest problem? The biggest problem is the restriction in the size. Can I make a piston out of it? No, it is not possible. Can I make a pin out of it? Maybe possible. Correct. So, that is a problem. So, here in sintering also, if you want to make something like an insert which is made out of metal matrix composite, possible. If you want to make a big hollow component, slightly difficult, hollow component. Difficult. Heavy, that means to say large, I mean it is not small, large hollow components, it is difficult. Next one is the hot powder extrusion. So, here what we do is we mix everything and then we try to do we mix metal, particulate and then we try to apply pressure, we try to apply heat and then the pressure is given through this ramp. We try to do an extrusion process through this. So, you can do a direct extrusion, you can do indirect extrusion. So, here what happens, we get a hot powder extrusion fabrication of metal matrix composites. So, MMC, if you want to make strong, light weight, high stiffness shaft, possible. These are the process which is used for making those outputs. Okay. There is lot of, if you take every process, we are just quickly browsing through the process. Each process has a fishbone diagram and each process has several parameters. These parameters have to be properly understood and then only we can try to execute it to get a good quality output. So, the next one is going to be in situ fabrication. So, in situ fabrication means, as I told earlier, so what happens is I try to add both these powders and there is a reaction which is happening, or I apply heat from outside. So, the the reinforcing and the matrix get evolved at the same time. Okay. So, in situ fabrication of metal matrix composite is a process wherein the dispersed phase is in the form of in the matrix results as a precipitate from the melt during its cooling and solidification process. So, this is what is in situ. So, I repeat, in which dispersed phase is formed in the matrix as a result of precipitation from the metal during its cooling and solidification. Okay. So, there are different types of metal matrix composite which are prepared by in situ. So, one is particulate in situ MMC, short fiber reinforced in situ MMC, and we have long fiber reinforced MMC. Particulate, it can be alumina, SiC, TiCN, TB2, TiN, whatever it is you can try to take. So, in particulate composite reinforcement, wherein which by in situ synthesis dispersed phase is in the form of particles, the examples are given here. So, short fibers, it is the same, you can try to have TiB2 whisker, okay, which is dispersed in titanium alloy, aluminum alloy, whatever it is. Then you can also try to have long fiber composites which are dispersed in situ in the form of a continuous fiber we disperse. So, we try to get the metal matrix composite of nickel, aluminum and NiAl matrix. These are all matrix which finds lot of applications in the aerospace in the application in aerospace industry. So, this is how it is in situ fabrication. So, we have heat which is getting applied. So, there is molten material which is there. So, we have initial alloy in solid state, we have unidirectional solidification MMC we have, and then what we have is a direction Q. So, what we do is we try to have initial alloy here and then we try to apply lot of heat. So, here there are unidirectional reinforcement whatever is kept here. So, this gets diffused and we try to form direction of crucible for the movement. So, that means to say from the bottom I remove and I try to take all the output and we get the required manufacturing. So, in situ fabrication of MMC is also gaining importance today. The major advantage, you can provide more homogeneous distribution as compared to the others. The bonding is very good and the equipments which are involved for making this is not so expensive like hot pressing, it is slightly economical. But the biggest problem is not everything can be done through this in situ fabrication method because of the material limitation. So, the disadvantages for this are the dispersion phase is limited by the thermodynamic ability of its precipitation in a particulate matrix. The size of the dispersed particles is determined by the solidification condition. So, these two I do not have a control. So, this is by my choice and not many materials give me this thermodynamic ability. So, the other second thing is the particle phase whatever I want, I cannot decide what is a particle phase getting formed, it evolves. So, I have to live with what is getting generated. So, with this I would like to finish the lecture on metal matrix composites solid state fabrication. I would like to continue with the co-precipitation in the next class. So, I would like to give you a small assignment. So, this assignment is you try to take wig or you try to take a cotton wig, okay, and immerse it in oil or whatever media you want, or it will be good if you do it in a color media. So, then what you do is you try to plot the then after you put it inside a bottle or a tank and then you put this wig inside. So, this is a liquid, okay, this is a wig, and then what you do is this wig will slowly start having by its capillary action, you can see the color of the oil just going, or color of the water going, or media going high. So now kindly plot it with respect to time, the height which is going high. So here you take two different types of oil. So what is this going to tell you? This is going to tell you what will be the influence of capillary action if I could capillary action of this wig to suck this liquid and then get inside. And then types, you take two different types of oil, or then you try to change the temperature of the oil. So types of oil will be, you try to take 2, and then you also try to take 3 different temperatures. Please plot it. Say for example, it's something like this. This can be at 30 degrees, this can be 50 degrees, this can be 90 degrees, whatever it is, and this can be oil A, type A, and this can be type B. So what are we trying to do in this entire small experiment? We are trying to see the influence of temperature on the capillary action. That is point number 1. 2, varying the media, varying the oil. So this what I am trying to link with metal matrix composite, varying density. So with this, you will try to realize what is the influence of the capillary action on the formation of a metal matrix composite. And then what do you do? Suppose if you want to accelerate, reduce the time to a large extent, if you want to change the viscosity to a very high viscosity, then what will you do? That is what you have to think and then do it. So we will catch you in the next lecture, which we will talk about co-precipitation or the other methods of metal matrix composite. Thank you.